Okay, so today we're going to go the other direction with alcohols. We're going to use them as starting materials, increase the oxidation state up to 2 or to 3. And again, that can happen in one stage or 2 stages. And we're going to learn some different conditions to do oxidations. We won't run through the exact mechanisms of those reagents, other than to what I'm showing you on the screen here is that an oxidation arises from an E2 process. So if we remember from Organic 1, E2 is bimolecular elimination. And the necessary requirements for an oxidation to happen, the carbonyl-carbon must have at least one hydrogen atom. So that's going to be the acidic hydrogen that is deprotonated during the elimination. So the oxygen atom is retained, but overall what's happening in all of these mechanisms, that H is substituted for something else that becomes a leaving group. And so typically we have some base in there that is going to abstract a hydrogen atom from the carbonyl-carbon. The electrons in that CH bond collapse to form a pi bond, so a carbonyl, and then the leaving group will leave. So overall, we're starting with oxidation state 1, shown in blue, and then we can end up with 2 or 3, depending on the conditions used. So going from an alcohol up to just the carbonyl in a one-stage oxidation, if we think about the functional groups necessary for that, if we start with a primary alcohol and it goes up to oxidation state 2, what functional group is it producing? So it's producing a carbonyl that's at the terminal chain, so that has to be an aldehyde. A secondary alcohol would have to be oxidized to what? A ketone, because the carbonyl is now on one of the internal carbons. You cannot oxidize a tertiary alcohol. It does not have an H on that carbonyl-carbon to eliminate. So primary alcohol to aldehyde, secondary alcohol to ketone, that's a one-stage oxidation. A primary alcohol is the only one that can undergo a two-stage oxidation. If that carbon goes from OS1 to OS3, what functional group is produced? So remember now that the carbonyl is at the terminal carbon. It's going up to oxidation state 3. So it has to end up as a carboxylic acid. So through that logic alone, we kind of know how to do these functional group transformations. So over the next couple slides, we're going to look at the reagents that accomplish that. So here's our oxidation state chart. So this line, or these empty cells, that is going to what differentiates us moving horizontally. If we start with an alkane, so ethane, and hypothetically we can oxidize a carbon up to a primary alcohol. So it's now at oxidation state 1. One set of conditions will oxidize that further to an aldehyde. See how this has 2 H's? So an H from carbon and H from oxygen formally get eliminated. That forms the carbonyl. The aldehyde still has an H. So it can be further eliminated and we can get to a carboxylic acid. So now we're at oxidation state 3. The other thing to keep in mind is how the hybridization changes. So the primary alcohol is sp3 hybridized. Aldehydes and acids are sp2 hybridized. And I want to bring that up because when you're looking at carbon NMR data, remember that the carbonyl carbon that's typically occurring between 170 and 220 ppm. Your sp3 hybridized carbon with that oxygen is typically about 40 to 60. So just by looking at the x-axis in a carbon spectrum, you can get a feel of what oxidation state is there. So hopping down the rows now, we're going to use this 3-carbon chain, so propane. And to show the difference, we're going to take that second carbon and oxidize it. So it's now a secondary alcohol. That carbon is sp3 hybridized. It still has 1 H left over. So that can actually go back or go up in oxidation state to a carbonyl, and now it's a ketone. Notice now at that point, that cannot be oxidized any further using the conditions we're going to learn today. Can you take a ketone and oxidize that carbon up to 3? Yes, you can. That's a separate sort of set of reactions that we'll learn in a different module. It is possible, and you do end up with a different functional group. So all of these reactions are basically tools that allow us to start, say, one functional group to another by adjusting the oxidation state. Notice the last example. If we were starting with this alkane that now has a tertiary carbon, it has an H. That can be oxidized to an alcohol, but from there it can't go any further because that carbon no longer has any hydrogens. It cannot do an elimination. So just by understanding the general mechanism of E2, that requirement for an acidic hydrogen, we're able to differentiate these different functional groups and predict what they will become. So our primaries can go to an aldehyde. That's just a one-stage oxidation. Or it can go from OS1 to OS3. That's a two-stage oxidation up to the acid. And one of the things I want to stress as we're thinking about this and you're doing problems, when you change these oxidation states, generate these new functional groups, how are you going to determine them spectroscopically? So the carbon NMR is one, IR is another useful one, because those carbonyl-containing functional groups all have a little diagnostic signature clue that you can pick out what it is. Secondaries only go up to ketones, and tertiaries we're not worried about. So here's 4 names of molecules, and the question says, which one of these cannot be oxidized? In general, whenever you're given a name, you want to draw out the structure, do some classifications, and then sort of apply the algorithm of which we're learning. So let's convert that name to a structure. I'm going to chop the name right there. And it starts off with butane, so that's 4 carbons. And it says at carbon 2 is the location of a hydroxyl group. Now that I have the parent down, I'm going to go back and do the substituents. So at position 2, there's a methyl. If we classify that, that's a tertiary alcohol. So the answer is going to be A. But let's use that logic for the rest of them. So here we have just that parent, 2-butanol. And so what class of alcohol is that? So that's secondary. If we were to oxidize it, what would it become? So that's going to be a ketone. And we can say that is what the product would look like. Then you can start thinking about how would you know that through proton, carbon, NMR, IR, that sort of thing. 1-butanol is just the isomer, so that is now a primary. If that went up just through a 1-stage oxidation, what functional group is that forming? So that's going to be our aldehyde. So we have oxidation state 1, 2, and because there's still a hydrogen there, that can go up now to 3. And so that is the acid oxidation state. And then the last one, that was 2-pentanol, so that's secondary, so that has to become a ketone. So just to kind of recap, your primary and secondary alcohols, in the IR, you're going to see that broad OH stretch. When the oxidation occurs, that goes away, and then you're going to see a carbonyl stretch between 17 and 1800. The difference between a ketone and an aldehyde, you got to look for that sp2 carbon H stretch. That's typically like 28 to 2900 reciprocal centimeters. That one can kind of get lost if you're not sort of aware of it. if a primary goes up to an acid, you're going to see the formation of that carbonyl, and then this OH is going to be there, but that OH looks different from the alcohol. So how do we actually do this? The three reactions that we see apply to both primary and secondary. And these are the one stage. Conditions. So a primary is always going to go to an aldehyde. A secondary is always going to go to a ketone. So the conditions, again, this is where we're going to start using abbreviations for things and names of the reactions. So PCC, I'll show you the structure on the subsequent slide. That's called pyridinium chlorochromate. A Swern oxidation, that's named after the person that discovered it. And then the Des-Martin periodinane. So regardless of what you use, the H of the OH gets activated, then an elimination occurs to form the carbonyl. So our first one is PCC, and that stands for pyridinium chlorochromate. The structure is shown below the arrow here. Pyridinium is a protonated pyridine, so that's a cation, and then the chlorochromate is this CrClO3 anion. So under these conditions, this H gets substituted for the chromium. That makes it a good leaving group. And then you have the carbonyl H, which is acidic. So H is gone, it's replaced by a leaving group, and then you do an elimination. And so that's how you end up with an aldehyde. As you might imagine, so chromium, where is chromium? It's right here. So in this class, we don't deal too much in the middle. These are the transition metals. Chromium is pretty bad for the environment, but it was one of the first sort of conditions discovered to do these. They're nice reactions to run in the sense that when the oxidation state of chromium changes, there's a color change. So these things will start off like kind of a dark orange, and then as the reaction progresses, it'll turn green and then brown, and then it'll end up as sort of a dark brown. And then you can be reasonably confident that the reaction's done. But you're still ending up with this chromium waste that has to be disposed of, and that's not good for the environment. So that is what has spurred on these other sets of conditions that we're going to see, things that are less negatively impactful. But I do want to emphasize, again, these are one stage. We're going to see another chromium reagent that's going to do a two-stage oxidation. But if we remember the difference between primary and secondary, once a secondary gets to the ketone, it stops. But if we use this other reagent with a primary, it's not stopping at the aldehyde, it's going up to the acid. So there is some nuance that you're going to have to be aware of when you start looking at these reagents, seeing them on the exams. So one of the first non-chromium sets of conditions that gained popularity is known as the Swern oxidation. So Daniel Swern was a professor at, I think, Temple University. And notice the conditions here. There's a lot of stuff that goes into this. There's this reagent called oxalochloride. And it has that structure. This other reagent called DMSO. So that stands for dimethyl sulfoxide, and it has that structure. Oxalochloride and DMSO will react with one another to give you this thing. So this is called a sulfonium chloride. That's the actual oxidizing agent. So you run this reaction, you let it stir for a certain amount of time, and then at the end we add a base, triethylamine. That's what initiates the elimination to happen in the mechanism. So because we're starting with a secondary alcohol at oxidation state 1, we can only go up to 2, and that's how we end up with a ketone. Any questions? So the third one is called the Des-Martin periodinane, or DMP. And again, whether we start with a primary or a secondary, it's only going up one stage. And so below the arrow, this is the structure of the Des-Martin periodinane. So what makes this an oxidizing agent, you see that iodine atom? So how many things does it have bonded to it? So we have 1, 2, 3, 4, 5. That's where this per comes from. It's sort of beyond the octet rule because, in the periodic table, it's in period 5, so it has these other orbitals that allow it to go beyond the normal octet. All this thing really is doing is replacing the H of the alcohol to make a leaving group. And so an elimination will happen from that carbon to the oxygen, and then we install the carbonyl. So in the reaction I've shown, a primary is going up to an aldehyde. If you had a secondary, it would go up to a ketone. So those are the three main conditions to to oxidize. And in the prior lecture, we learned about reductions. So if we start putting all this together, if we take this one butanol to make butanal, if we wanted to now make, we start with a primary, we have an aldehyde. If we wanted to make a secondary alcohol, we could take that aldehyde, add a Grignard to it to do a nucleophilic addition. So for example, if that was our starting material, and we wanted to take this Grignard reagent, that would add to the carbonyl. Then we could do a workup. So overall, that step is a reduction, but now we've ended up with a secondary alcohol. Then you might imagine we could oxidize that to a ketone, add some other group to it, and we would end up with a tertiary alcohol. So really now in this module is where we start learning these reactions to sort of expand where we can go in synthesis land and learn about making pretty much any molecule that you can dream of. So those were all one stage. What I want to talk about now is a two-stage, and this only applies for primary alcohols going up to carboxylic acids. So how does this work? As we can see from the aldehyde, that aldehyde only has one oxygen, but a carboxylic acid has two. So where does that second oxygen come from? So I'll show you this in two parts. We can see from just counting sigma plus pi, we're at oxidation state 2, and that belongs to a carbonyl. Carbonyls can undergo an equivalent reaction where the oxidation state stays the same. So it's still 2, but now notice the pattern. You have a sigma and a sigma. So that carbon is now bonded to two OH groups. And that functional group is called a hydrate. So the difference between the aldehyde, again, we have one oxygen, now we have two, and that is what is required for a carboxylic acid. So on the next slide, I'll show you this mechanism of how that forms. And essentially, under the two-stage oxidation, the aldehyde is converted to this hydrate, and the hydrate then goes up to OS3. So if we recall our definition of oxidation reduction, oxidation is when that number increases, reduction is when it decreases. If it stays the same, so 2 to 2, that's just called an equivalency. And why does this exist? An aldehyde and a hydrate are obviously different functional groups, and they will have different reactivity. This one is special because we'll see quite a bit of it when we get to module I think 6 with biomolecules. Carbohydrates have that sort of carbon with 2 sigma bonds to oxygen. And that's what allows sugars like glucose, things that you've heard of, it allows them to exist in a specific form that's stable, and that's how nature has kind of evolved. But the take-home message here is if that is staying the same, these things now have different reactivity properties. So how do we form that? And we'll look first here at acidic conditions. So the blue number is oxidation state 2. And that's called a hydrate. So what's the difference in molecular formulas from the product to the starting material? We've hydrated, we've added the elements of H2O to that carbon. So we know that hydronium, H3O+, is an acid. So this thing has to be a base. The action of a base is to abstract a proton, and we have electrons on the oxygen. So we'll protonate that oxygen. So if you're going on to, say, biochemistry or anything with cellular and molecular biology, proton transfer reactions, this first step that I just drew, those are pretty important because under physiological conditions, proton transfers are handled by amino acids. You're moving that proton around to activate things. The oxygen is now activated. And I want to show a resonance form where that plus charge moves down to carbon. So we're going to give oxygen its lone pair back. That means the carbon has to be plus. So it is now an electrophile. And the water is a nucleophile supplying electrons. So those will attack. We shuffle around the plus charge. Then the last step is just a proton transfer. And we're going to use water to do that. Because then that will regenerate the hydronium ion. So the hydrate is the reactive starting material to go up in that oxidation state to acid, because now we have the 2 oxygens required. One of them will get activated by substituting that H, and then we have the acidic proton to do the elimination. That gets the carbonyl, and then it's still bonded to OH, so that's the acid. So the two-stage oxidation is just commonly called a Jones oxidation. We use a solvent acetone. So that's that ketone. Remember, it can't do anything. It can't be oxidized. That's the solvent. We use chromium trioxide, and sulfuric acid will react together to make this thing called chromic acid. So H2CrO4, that's chromic acid. And this is the kind of nuance that I want to draw your attention to. Sulfuric acid in the most concentrated form is 98%. The other 2% is water. So when you start with a primary alcohol, it's going to the aldehyde. The aldehyde does the hydration, and then that gets oxidized up to the acid. Under those PCC conditions with pyridinium chlorochromate, there was no water present. So the hydrate cannot form under those conditions. So it has to stop at the aldehyde. So practically speaking, if you're in the lab doing this, you can really only carry this reaction out if that is what you're trying to accomplish. If you have other functionality in there, these conditions are really harsh. You have a strong acid, a strong oxidizing agent. It's going to start to do other unwanted things to the molecule. So again, how do we know we got the acid? The IR is going to have the carbonyl plus that accompanying OH that looks different from an alcohol. Our sp2 hybridized carbon is going to be between 170 and 220, so we'll know that. And so again, from all these different pieces of data, you can kind of figure out what conditions were used. An alternative to the Jones oxidation, and this is less, I would say less commonly used, is potassium permanganate. So that's shown here, KMNO4. Under aqueous conditions, that will also do a two-stage. So 1 to 3. I don't know, maybe in Gen Chem you might have seen potassium permanganate. So if you take that solid, dissolve it in water, it makes this purple solution, and inevitably you're going to get it on your clothes and have purple spots everywhere. It's kind of messy to deal with in that regard. The other thing I want to draw your attention to is, as you're preparing to take the final exam, that reagent we saw before, it will react with alkenes to make 1,2-diols. So that's what I meant by, if you have these different functionalities that will react with one reagent but give different products, you have to sort of design your sequence so you're not getting a side reaction or some other functionality you don't want. So it says, which of the following alcohols can be oxidized to the carboxylic acid with chromic acid? So we'll draw the structures, then we'll classify them, then we'll see what's good. So 2-butanol. One methyl cyclohexane, 1-ol. Two methyl butane, 1-ol. And then 2-methyl, too many carbons there. 2-methylpropane 2-ol. So let's just classify them. We have a secondary, tertiary, primary, tertiary. So we know already tertiaries don't do anything. A secondary, even though that chromic acid is a 2-stage oxidant, it has to stop at the ketone. So the primary is the only one that can go up to the acid. Questions? So I think that is going to wrap up oxidations. So the next couple slides are going to be about, we know alcohols, we know how to make the carbonyls of them. What are some reactions of alcohols? So some things where we retain the oxygen, meaning we're substituting the H for something else, or we're removing that oxygen completely. So we started off the module by saying that the hydroxyl group, we have this ambiphilic reactivity. So the OH can be acidic, meaning we can deprotonate it. Therefore, the oxygen is nucleophilic. Or we can use the oxygen as a base. It can be protonated, and then therefore it's an electrophile. It can leave and be substituted. So again, under these conditions that we see, one thing you can do is make note cards about how does the reagent affect the OH group. Is it sort of substituting that H for something else, or is it displacing the OH group completely? The first one here is we're going to take advantage of the acidity of that H. So our alcohols have a pK of about 15 to 18. So we're going to substitute H for some other group that's now inert. And so this is called a protecting group. From the starting material to the product, we're generating an ether. It's called a silicon ether because the oxygen's bonded to a carbon and a silicon. So a silyl ether. And really what that silicon is doing, it allows us to retain the oxygen in the molecule, but since there's no H, we've removed that acidic functional group. So the reagent tert-butyl dimethyl chloride plus a base allows us to do that substitution. And why do we need the base in there? So see that H in that Cl? That generates HCl, which is an acid. The amine base neutralizes that. So how would we use that? Say you have this alcohol and you do not want it to be oxidized. We've taken the H, we've put something on there that can no longer react under oxidation conditions. So we have to retain that. So that's a protecting group. Typically with protecting groups, you put them on, you do some things, and then at a later step, you have to remove it. So the deprotection uses this reagent here called TBAF, which stands for tetra N-butyl ammonium fluoride. It's a salt. So you have a cation and an anion. The fluoride anion likes silicon. So overall, this is an SN2 reaction. Fluoride attacks the silicon, we break that bond, and then that restores the H of the alcohol. So two things we learned today about protecting. A carbonyl group can be protected as a hydrate because we're maintaining the functional group equivalency. And then an alcohol can be protected as an ether. Okay, so the next two reactions, what you'll notice so I'm highlighting the carbon bearing the OH. Under these conditions, that OH group gets substituted. So for this reaction and the next one, we're substituting with a halogen because that's a heteroatom. That oxidation state on carbon is still retained. So if we want to transform an alcohol OH into a chloride, we can use this reagent called thionyl chloride in the presence of a base pyridine. And then our solvent is dichloromethane. So what is it good for? If I put those lone pairs in, that's the polarity of that bond. So it's a secondary chloride. We can do SN2 reactions with that. So we can substitute that chlorine for other things we learned in Organic 1. And what we saw recently, we can invert the polarity. So if we treated that with magnesium in diethyl ether, that can make a Grignard reagent. So that's one way of making them. We can then take that, add it to some other carbonyl, and then we can start making alcohols. So another study tactic you can use is to sort of make these like mind maps where you have a functional group sort of in the middle. And from that, you sprout off what is the transformations it can do. So an alcohol to a chloride, and chloride SN2, chloride to Grignard. What are all the things you can do with these tools? So for the next two, we'll run through some arrow pushing just so you can get some practice on that and see how this transformation happens. So there's the two main things we need, the thionyl chloride and the pyridine. I'm not drawing the solvent because it doesn't participate. It's just there to sort of dissolve stuff. Even though the H of the alcohol is acidic, it has a pKa 15 to 18. The pyridine is a base. That base is not strong enough to deprotonate that. So the first thing that happens is a lone pair on oxygen will attack that sulfur. So sulfur gets attacked, we break a pi bond, we get this intermediate. We've balanced off the charges. This oxygen's minus, that one's plus. And from here, we have to get a chlorine off the sulfur and then have it attack. It needs to get rid of the oxygen bonded to carbon. So if we collapse this back down, that forms the pi bond. It's going to allow us to eliminate Cl minus. We've still balanced our charges. So chlorine's now minus, the one oxygen's retaining the plus. So we have a good nucleophile. The oxygen is now activated for displacement. So there's our desired product. We end up with this other thing, and we still haven't invoked why the pyridine's in there. We have an OH group that's now pretty acidic because the oxygen's bonded to sulfur. So it will abstract that. This bond is now going to form a second pi bond to sulfur. In doing so, eliminate chlorine. So the nitrogen ends up with plus. It's balanced off by Cl minus. And then we're producing SO2 gas. So these conditions are pretty harsh as well because thionyl isn't the most pleasant thing to work with. Kind of smells a little bit, but SO2 gas is very toxic in the sense that if you have any sort of metal stuff in your chemical fume hood, it's going to start degrading it pretty fast. So really, when you run these, there has to be some trap that neutralizes the production of that. So we've made a what's kind of abbreviated as FGT, functional group transformation. A different set of conditions. Instead of making chlorine, we the bromines. This uses PBr3, phosphorus tribromide. Notice under nitrogen, so we know nitrogen takes 3 bonds, so phosphorus is under it. So it's going to take 3 bonds as well. So the phosphorus will have a lone pair. We have 3 bromines, which are electronegative. They're all tugging on the phosphorus. So it's electrophilic. Now, the same thing's going to happen where that oxygen of the alcohol attacks it. That's going to produce a Br minus. That's a leaving group that will come back around and then just get rid of the oxygen. So overall, again, we start with OH, and now we've substituted it for Br. So anytime I see PBr3, I think of Pabst Blue Ribbon. I'm from Wisconsin, so that's your watered down crappy beer people drink. And so we're starting with beer. So how does this one happen? Oh. In terms of the stoichiometry, you see how the phosphorus has 3 bromines. So for every 1 equivalent of that, you're going to produce 3 of this. So you can think of it that way, or think of it as, so for every 1 mole of that, you only need 1/3 mole of that. And this is a pretty nasty reaction as well, because phosphorus tribromide, as soon as you open the bottle, it's going to start fuming because it's reacting with the humidity or moisture in the air. and it's kind of ruins stuff in the lab. But anyway, the oxygen will attack phosphorus. So in our mechanistic rules, we're forming a bond, so we're going to break a bond. Since oxygen got another bond, it's plus. Br got its last set of electrons, it's minus. So that will attack the carbon bearing the oxygen to displace it. So mechanistically, that's an SN2 reaction that's happening. So you're left with this intermediate here that still has two bromines. That's why it can react with two more equivalents of your alcohol. And eventually it's going to produce, I'm going to cheap out here and draw it that way. So that'll be some form of a phosphoric acid. When we get to the last module of this semester, we're going to look at a little bit of the chemistry of phosphorus because we'll think about why nature chose phosphorus to be included in DNA. So DNA, you have, this sugar that is linked through phosphorus at a certain oxidation state. And that's something that, because of the row it's in, this row, nitrogen, which we've seen the most of, it can't get to the oxidation state that phosphorus can, which allows DNA to be stable. So as we're scanning across the periods and up and down the groups, we want to start thinking about how oxidation state matters ultimately towards these biomolecules. So finally, the last of these sort of activations for what we've seen so far in oxidation reactions and then the chlorine and bromine reactions, we can never just displace OH. So for example, if we had that same alcohol and we just treated it with sodium bromide, this reaction, this SN2 reaction, would never occur because the OH group is a bad leaving group. So chemically, what has to be done? That H has to be substituted for something that then makes the oxygen want to leave. So if we want to generalize the last two sets of conditions where we had chlorine and bromine, we can generalize it by activating H into this thing called a sulfonate. So the H has become this big group here. And now overall, that whole thing, including our alcohol oxygen, is a good leaving group. And that allows us to access a starting material that we can do SN2 chemistry with. So to make these sulfonate esters, we use a reagent called a sulfonyl chloride. So I'm just going to highlight this part of it, sulfonyl chloride. Then in blue, the blue is whatever other group is attached to it. It can be a couple different things, but the main part of that functional group is the SO2Cl. So we have H and then we have Cl. So a byproduct of these reactions is HCl, which is an acid. So therefore we have to run the reactions in the presence of a base that neutralizes that. We start with. So how do we get this to happen? What are some of the arrow pushings? The H of the alcohol is not acidic enough for that base to deprotonate it. So again, the oxygen is going to attack the sulfur directly. So it's going to do an addition. We're going to break a pi bond to get to an intermediate. So oxygen attacks sulfur. We break a pi bond. So sulfur can again expand its octet because it's below oxygen. At this point, we'll do an acid-base reaction. So that oxygen will end up happy. So we've balanced our charges, and now the final elimination where this comes back down to push out the chlorine. That gives us our desired product. Plus that amine salt that traps the HCl. So that's a good leaving group for SN2. So now we can start substituting that for any other nucleophile that we know. So I think on the next slide, we'll run through the list of what those things were that we saw in organic 1, and then just a little bit about their IR signatures. So in the first reaction, I said, that thing attached to the SOCl2 can be sort of anything. These are two examples of that. This first one here, trifluoromethyl, that's, when you put that on, that's the best leaving group that you can get for organic chemistry. Because now you have a carbon with 3 electronegative fluorines. It's helping to stabilize that leaving group. This other one has a benzene ring. And so in the first couple modules of this semester, we learned about conjugation and aromaticity. So the reason these are used is because now when you do the reaction, you can actually see it under UV light that it's forming because you have a chromophore. The ones with methyl and CF3, those are a little bit harder to determine are you actually getting it on the OH group or not. So we'll wrap up in the last 2 or 3 minutes here by considering a sequence, because you know a lot of reactions now. Can we predict what's the product of each step, and then ultimately what's the final product? So it says we're going to take 2-butanol. So we want to draw that out first. And then we have a 4-step sequence. We want to predict what the product is. Step number 1 is PBr3. That's going to take OH to bromine. So there's the polarity of that bond. Step number 2, we're treating with magnesium and diethyl ether. That's going to invert the polarity and make a Grignard. So that's a carbanion. Step number 3, we're treating with an electrophile. So ethylene oxide. That's going to attack a carbon, pop the ring open. That generates this alkoxide, and then step number 4 is going to protonate it. So overall, the name of that product, we have a primary alcohol. It's 5 carbons long, so we can eliminate B and C. The alcohol is at position 1, so we really can't decide based on A or D. And then the location of that methyl group is on carbon 3, so choice D is going to be the correct answer. So we are out of time, but that is what we're going to start doing as we learn these reactions. With starting material, apply a bunch of sequences. What do we end up with? Or alternatively, if we're given a product, how can we design a sequence to think back to some starting materials to make it? So let me just get to that, then we'll hop back to those other 2 slides. So there's your starting material. We have a good leaving group. these were some of the main functional groups that we learned from Organic 1 that are good nucleophiles. Remember, for SN2, we need a polar aprotic solvent. That's what these are. And then once that substitution happens, so here's your leaving group. Here's your nucleophile. Then you can see it's been substituted. So the first one, if we use potassium cyanide, that generates a CN triple bond. That's a nitrile or a cyano. Since it's a triple bond, we see a sharp signature in region 2 of the IR. There's one nitrogen, so the parent mass will be odd. And then we'll see an sp hybridized carbon in the carbon NMR. So when you go down the list of all these nucleophiles, you can see what are their diagnostic IR mass spec or C13 signatures that you know that nucleophile was used.